All right, so here is an example of simple harmonic motion when you're given a position versus time graph. So for this particular problem, we're given this graph here where the position is given in units of centimeters and time is given in units of seconds. And it wants us to find all these different parts, okay? So if you need to, pause the video and then write these parts down so you can kind of follow along as I take each part one at a time. All right, so go ahead and knock it out. All right, so to do part A and B, here I've given you a visual as to what's going on. If you look at this particular position versus time graph given, hopefully you recognize that the object starts at equilibrium, and that is because at time is equal to 0, x is equal to 0, which implies the object is at the equilibrium. Now, as to determine which way the object is going, left or right, you have to look at the tangent line at time is equal to 0. So in this particular graph, if you look at the tangent line at time is equal to 0, you know that it is a positive slope, which implies that the object is moving to the right. And in this case, if it's moving to the right, I have an arrow here to the right of the diagram here. That is V. And notice here that the subscript here for V is V max because at the equilibrium point, all of the potential energy stored in the spring must be converted to kinetic, which implies that the speed is maximum at the equilibrium point. All right, so let's go ahead and do part A. All right, so to do part A, you need to know the function for frequency, and frequency is simply just 1 over capital T, where capital T represents the period for one cycle. So according to this graph, if I start at the origin and I trace my cursor all the way up there, that makes a sad face, which is a half of a circle. And then I trace out another half of the circle, which is the smiley face. That completes a full cycle. A circle has a happy face and a sad face. And I just did that and I stop at 4 seconds. Okay, so the period for this particular graph is 4 seconds. So if we just plug and chug one cycle and that phenomenon took 4 seconds. So if you reduce it down to a fraction, that gives you a value of 0.25 hertz. Let's do part B. Part B asks us to find V max. Hopefully by now you know V max is A omega. We know A from the graph. A is simply 2 centimeters given in the function here, and omega can be broken down into angular displacement over change in time. Which angular displacement you use, that is totally up to you. Again, I like to use 2 pi because it's easier to visualize from the graph where a complete cycle starts and end. In this case, the graph starts at 0, so I need to go all the way to 4 seconds. That gives me a full cycle, which completes a half and then a half based on what my cursor is tracing out. So that's a full cycle. If I do that, I know that change in theta is simply 2 pi because the unit for one cycle, one revolution in radian is 2 pi rad. And then change in time here to me is just 4 seconds because I've chosen to use a complete cycle. Okay, so whether you use pi or 2 pi or pi over 2 or 3 pi over 2, it doesn't really matter. Just make sure that your time is consistent with your choice. Here, my time is consistent because I chose one cycle. One cycle is 4 seconds. And then the amplitude is simply given in the graph as 2 centimeters. And if you do calculator work here, a little cancellation if you like, but if you do the calculator work, you should get a value of 3.14 centimeters per second. And another way to do it, which is pretty much the same as the previous one, but sometimes folks don't recognize that it's kind of the same because functions are substituted for. But we know Vmax is A omega, but omega is simply 2 pi over capital T. But capital T, if you write it out, capital T is simply equal to 1 over F. So if you do the substitution and you multiply by the reciprocal, you can simply say that omega is 2 pi times the frequency. But we already know the frequency for part A. We know the A from the graph. So really here it's just another plug and chug situation. All right, so A is 2 centimeters, 2 pi gets carried down. The frequency, I kept it as 1/4 here, which is pretty much 0.25 hertz over there. So if you do that, you'll get a value of also 3.14. Again, if you'd like to cancel stuff out where and when appropriate, but you don't have to. Just plug and chug in your calculator if you need to. All right, let's do part C. Part C asks you for the magnitude, so it doesn't really care for the direction here, of the maximum acceleration in centimeters per second square. Because it wants it in centimeters per second square, I do not have to convert units here in centimeters to meters yet. All right, so let's do part C. We know that the maximum acceleration is given by this function a, aka amplitude, angular frequency square. We know both these values. Again, a from the graph is given as 2 centimeters. We can break down once again omega into angular displacement over change in time. We square it, and if you make a choice, I made a choice. I again will use 2 pi because it's one complete revolution. The time for that phenomenon to occur is 4 seconds, and then I can simply carry a down from the graph, which is 2 centimeters. And do not forget the square once again. And if you do your calculator properly, you can reduce 2 pi over 4 down to just 1.57, and that'll be rad over second. And then you can square that and then times it by 2 centimeters in the front there, and you should get a value of about 4.93 centimeters per second square. Again, I will leave it there because that's what it asks for, centimeters per second square. Let's go part D. Part D asks us to find the velocity in centimeters per second when it is 1.5 second. So I'd like to point out that if you don't know this graph, it's a sine graph. Hopefully I can just knock this out real quick. I gave you the parent graph of a sine function to the right here just for you to help you visualize. A sine graph starts at 0. And in this particular case, it is a positive sine graph because it first curves upward and then it dips into the negative region, which mirrors what you're given here. The graph that you're given in this case is a sine graph because it looks like the sine of x parent graph. Okay. So a sine graph starts at 0. In this case, it's positive sine because it first goes up and then it goes down and then it goes up again, which mirrors a positive sine graph. So if you know that, and if you know a little bit of calculus, to find the velocity, you first have to take the derivative of your x to t. In this case, the derivative of sine would just simply give you cosine, and then you have to do chain rule and then take the derivative of omega t, which gives you omega, and so on and so on. But you don't need to know calculus. You can just write this function down in the AP Physics 1. All right, to go ahead and solve for v of t, I noticed here I expanded the function. It says velocity here at 1.5 seconds. And then from here, we know a is 2 centimeters from the graph. We know omega, I've chosen to use 2 pi rad over 4 seconds. And then here, omega in the side of the parentheses as well is 2 pi rad over 4 seconds. And I plug in time as 1.5 seconds because that's what it wants. But I do want to point out, this is usually where students will kind of go wrong, is that they don't pay attention to the units. They'll write stuff out without units, and then they end up using the wrong mode on their calculator. So you notice here, inside this parentheses after cosine, it is 2 pi rad per second. So it's important that if you apply the strategy, you need to make sure that your calculator is in radian mode. Because if you're not in gradient mode and you're in degree mode, keeping this value, you'll get some whack answer, okay? So make sure you write your units out. If you want to keep it in rad per second, make sure you switch your mode in on your calculator, to radian. If not, you will get some messed up answer. So make sure that happens first. All right, so from there, once you do that, you can just simplify. Here, I've simplified cosine of 2 pi rad over 4 times 1.5. If you put that in your calculator, it will give you a negative value of 0.707. And if you just simplify further with your calculator, you should get a value of negative 2.22 centimeters per second. And this makes sense based on the graph. All right, the time interval here is the instantaneous time here is 1.5 seconds. So if you go up to the graph where my cursor is, 1.5 seconds there, if I trace it up, that it meets that particular point on the graph. So that particular point has a negative slope, and my answer is negative, and it's negative 2.22, which makes sense because here for this particular problem, the minimum speed is 0 and the maximum velocity, it's about 3.1. So my value here lies between that range, and it is negative, so it makes sense or is reasonable. Okay, so I encourage you, as you do practice problem, make sure your answer is reasonable before you move on. And let's go part E. Part E asks us to find the time when the position, aka x of t, is a fourth of the amplitude. So let's go ahead and bust out our x of t function. Again, as I mentioned in the previous slide, by looking at the graph, you have to recognize that this is a sine graph, and it's a positive sine graph because 1, it starts at 0, 2, it starts in the positive region, and then it dips down. All right, so x of t here is simply a sine of omega t. It's sine because the graph starts at 0. All right, so from here, we can just substitute x of t for a over 4 because that's what part E says. it says when the position is 1/4 of the amplitude. So A over 4 is the same thing as 1/4 of the amplitude. And then I plug in omega, which is 2 pi rad over 4 seconds times the time. Here, your time is your unknown variable. Again, you have a on the left side, you have an a on the right side. So I will go ahead and simplify that. And then this looks like this next. To solve for t, which is inside the parentheses, you first have to do algebra properly. You have to get rid of the sign on the outside. To get rid of the sign, we do inverse sign. Okay, so here this explains the inverse sign on the left side. And then you notice here, the sign on the right side will cancel out because we just got rid of it. And then on the right side, you simply have just 1.57 rad per second times t. So if you punch in your calculator, inverse sine of 1/4, and then that will look like this. You should get a value of 0.253. And then to solve for t, we simply divide both sides by 1.57. And if you do that properly in your calculator, you should get a value of about 0.161 seconds. All right, let's go to part F. Part F asks us to find the spring constant in newtons per meter. So if you know this particular function, the period of an oscillation is 2 pi radical m over k, where m is the mass of the block or mass of the object that's being oscillated. All right, and k is your spring constant. So here, we know everything already. We can pull t from the graph. We know m because it's given us 1. So the only thing missing here is k. So to do this properly, let's go ahead and square both sides. Squaring both sides leaves us with t squared. 2 squared is 4. Pi squared is pi squared. And then squaring both sides simply gets rid of this radical sign that's over m over k. So that simply just get rid of the radical sign. So I just carry m over k down. And then from here, to solve for k, we move k up to the left side. We move t squared down to the right side. And that will look like that. Here it's just plug and chug. 4 is a constant. Pi is a constant. Square that. M is just 1, which makes this particular part easy. And then time here is just 4 seconds. So if you plug all that in your calculator, you should get a value of about 2.47 newtons per meter. And newtons per meter is the unit it wants in, so we are done. All right, part G. Part G asks us to find the speed when the particular object is 0.2 centimeters away from the equilibrium, whether it's on the left side or right side. It wants speed, so it doesn't really matter whether it's moving left or right. But to do this particular part, you have to recognize that you need to use conservation of energy. Okay, so here I have set up. First, the spring is compressed or stretched. It doesn't really matter. But we know that there's a certain amount of PE, or aka energy stored in the spring. Okay, so here I have it where I have made a statement. The potential energy stored in the spring initially must be converted to KE and PE of the spring. Here we notice that it says 0.2 centimeters away from the equilibrium, which implies that the string has not fully uncompressed, which means there's still some energy stored in the spring. So we need this second PE term on the right side of the function. All right, so from here, we just expand it to what it is. PE spring max is simply 1/2 Ka squared, where A is the amplitude, the amount of distance that the spring has been stretched or compressed. Okay, and then Ke is simply 1/2 mv squared. And then PE spring is 1/2 Kx squared. X in this case being the distance from the equilibrium, which is given in the problem as 0.2 centimeters. All right, so if you recognize this, we can cancel the 1/2 out because it appears in every term. And then from here, we're simply left with Ka squared equals mv squared plus Kx squared. But then we're solving for v, so let's go ahead and move stuff and clean up a little bit. I will move the Kx squared to the left side, which makes it negative. And here I notice this is Ka squared minus Kx squared. You don't have to, but you could just factor out k, which I will do. Okay, so here I can just factor out k because both these terms on the left side share a k. And then from here, I know this on the right side is v squared because as you carry this down, keep in mind that that is v squared. We know what k is from our previous part. We know what a is, and then we know what x is. We know what m is. So let's just go ahead and plug stuff in. I do want to point out, however, that the unit for K here is newtons per meter. And it's important that you understand and write out stuff as you practice. A here is 2 centimeters. Centimeters does not match with meters in the spring constant unit. So therefore, it's important that you convert the amplitude, which is 2 centimeters, to meters. And so 2 centimeters is simply 0.02 meters. And then you also need to convert X, which is given in the statement as 0.2 centimeters. But you have to convert it to meters, otherwise the unit in the spring constant will not cancel out. Okay, so that's why these values that I have on the screen here is 0.02, which is your amplitude in units of meters, and then the distance away from the equilibrium can be converted to units of meters as well. So zero point 0.2 centimeters is simply 0.002 meters. You square all that and then divided by a 1, which is redundant, but I put the 1 in just as a placeholder so that you know the mass value is indeed 1 kilogram, which is given in the statement. If you do the left side, all the calculator work, and then to solve for V, we gotta square root it because this is V squared on the right. So if you do that, you should get a value of about 0.03 meters per second. And that is it. Okay. All right. Stay nerdy. Don't be whack.